Inertia is a concept wherein a body at rest continues to remain at rest unless compelled by an external force. Similarly, a body moving at a uniform speed continues to move at the same speed unless an external force acts on it to slow it down or to make it move faster. Without friction, the skater would move with a uniform velocity indefinitely. It is because of friction that we come to a stop. If you are standing on a stationary skate and the skate starts moving suddenly, you would feel a jerk. Since your feet are in contact with the skate, they move along with the skate, while at that instant your head is stationary. This causes the body to jerk backwards. Imagine the moving skate hits a small wall. At the instant just after the collision, your feet come to rest as they are in contact with the skate. However, your head is still moving with speed before collision. This causes the body to jerk forwards. Galileo stated that in a frictionless world, a ball bearing in a U-tube would move to and fro endlessly. This is by law of conservation of energy. Now, using the slider, try reducing the angle below 90 and observe the movement. It would still move to the same height. Galileo argued that the same should apply when the angle is 0. This means that the body will keep moving endlessly when no external force acts on it. Inertia is a property of the body to resist change to its state. Inertia is directly proportional to the mass of a body. The heavier the body, the harder it is to move it. We say that the heavier body has more inertia. Inertia is a property of the body to resist change to its state. Inertia is directly proportional to the mass of a body. The heavier the body, the harder it is to move it. We say that the heavier body has more inertia. The heavier the body, the harder it is to stop it when it is in motion. We say that the heavier body has more inertia and is more difficult to bring to stop than a lighter body. Acceleration is caused by unbalanced forces. A car accelerates when the engine force is greater than the frictional force. When all forces are balanced, there is no acceleration in the system. This is a very important concept. There can be motion without a force. According to Newton's first law, without any external forces, a moving body will continue to move with the same velocity endlessly. In the case of the car, when the engine force is greater than the frictional force, the car will accelerate. When the engine force is less than the frictional force, the car will decelerate and come to a stop. But when the engine force is equal to the frictional force, the car will keep moving with the same velocity. If you apply a force to a body, it will accelerate. If you double the mass of the body, the acceleration will halve. You can try this by changing the mass using the slider. Acceleration is inversely proportional to the mass for a given force. If you apply a force to a body, it will accelerate. If you double the mass of the body, the acceleration will halve. You can try this by changing. If you apply a force to a body, it will accelerate. If you double the force applied, the acceleration will also double. You can try. If you apply a force to a body, it will accelerate. The acceleration of a body is the ratio of the force applied and the mass of the body. The acceleration is directly proportional to the force applied and inversely proportional to the mass of the body. So, Newton's second law states force is equal to mass times acceleration. Newton's third law states that action and reaction are equal. When a bird flies, it flaps its wings to push the air behind it. The air reacts by pushing the bird with an equal force. That is what moves the bird forward. In the case of the fish pushes the water behind using its fins. The water reacts by pushing the fish forward with an equal force, which moves the fish forward. Action and reaction act in pairs. To find out the acceleration of the bird, you have to consider forces which act on the bird. So, the force on the bird in this case is the force by the air on the bird. If you divide this force by the mass of the bird, you will know the acceleration of the bird. Do not make the common mistake to include forces by the bird on the surroundings. Only consider forces on the bird. Momentum is a product of mass and velocity, so it is directly proportional to both mass and velocity. If you increase the mass, you increase the momentum. Similarly, if you increase velocity, you increase the momentum. Momentum is a product of. To change the momentum of a body, an external force has to be applied. In the case of the car, to bring the car to a halt, an external force has to be applied. The greater the force, the less the time for which you need to apply the force. To change the momentum of a body, an external force has to. This is a variation of Newton's second law of motion. Force is mass times acceleration, and acceleration is the rate of change of velocity. If you look at the equation, you will now notice that mass times change in velocity is the change of momentum. So, force can also be described as the rate of change of momentum. Or in other words, force times the time for which the force acts is the change in momentum. The change in momentum is called impulse. It is the mass times the change in velocity, or the force times the duration for which it acts. Consider a catcher holding on to a catch. The change in momentum is the mass of the ball times the velocity with which it was traveling before the catch was taken, since its speed after the catch was completed is 0. In the first scenario, the catcher hardly has a follow-through, so he has to apply a higher force for a lesser period of time to stop the ball. If you tick the box using less force, you will see that now, since the time taken to stop the ball was much higher, he uses less force. But in both cases, the impulse of change in momentum is the same. In both cases, with or without a follow-through, end up using the same force. But when you follow through, the contact time between the catcher and the ball increases. This increases the impulse as it is the product of force and time of contact. So, the change in momentum will increase and the velocity of the ball in the reverse direction will increase. This decreases the speed of the ball. When a bug hits the windshield of your car, is it that the car applies a higher force on the bug? No. By Newton's third law, the force of the car on the bug is the same as the force of the bug on the car. So, the collision forces are the same. If you divide the force by the mass of the bug, the change in velocity would be very high, since the mass is negligible. For the car, the change in velocity due to the collision would be negligible, since in comparison, its mass is very high. The passengers in the car would not feel the deceleration. Consider the two scenarios: a glass falling on a hard wooden surface and on a carpeted floor. The change in momentum is the same in both cases, since the velocity of the glass before the collision is same in both cases and after collision is zero. The carpet increases the time of impact between the glass and the floor, which means that the force on the glass is less. That is why the chances of a glass breaking on a hard floor is greater. The law of conservation of momentum says that the momentum of the system remains the same. In this case, the system is the cannon and the ball. So, the initial momentum is zero. After the ball is fired, the system momentum is the addition of the momentum of the cannon and the momentum of the ball. So, in order to bring this to zero, the cannon will travel with a velocity in the opposite direction to the ball, with a lower velocity than the ball, since its mass is greater. Impulse is the change in momentum. When you consider a bouncing ball, remember that the change in momentum is the mass times the change in velocity. If you consider the velocity just before impact as positive, then the velocity just after impact is negative. So, when you compute the change in momentum, it will be the additions of the momentums before and after the collision. The ball which bounces to a greater height is the one where the impulse was higher. The law of conservation of momentum can be applied to collisions. In this case, the system is both the balls. So, the initial momentum is zero. After collision, since both balls are moving and have the same mass, their velocities should halve to conserve momentum. The momentum before collision should be the same as the momentum after collision. Before collision, if the velocity of the truck is considered positive, then the velocity of the car would be considered negative since it's in the opposite direction. On computing, you will notice that the momentum of the car and truck is the same, but the signs are opposite. Since the change in momentum for both the car and the truck is identical, and the duration of collision is also the same, the force of impact is the same for the car and the truck. The sailboat along with the fan is our system here. So, momentum has to be conserved since there is no external force. This means whether the fan is on or off, the mass of the system remains the same, and therefore the velocity also must remain the same. If the fan was not in contact with the boat, then we can consider it as an external force, and in that case, the velocity would increase. weight is mass times gravity. The mass of the person, whether on Earth or the Moon, is identical, but the gravity changes since it depends on the force of attraction, which is less on the Moon since the mass of the Moon is less than that of the Earth. Weighing machines indicate the weight and not mass. This means you will weigh less on the Moon compared to the Earth. The scale reading represents the normal force upwards. So, if you are stationary, you get your exact weight. But if you are moving in an elevator, the normal force would change, and so would the scale reading. If you accelerate up in an elevator, you will notice that the scale reading will increase. Whereas, if you accelerate downwards in an elevator, the scale reading will decrease. If a cable snaps in an elevator, the elevator will also have a free fall, just like you. In this case, there would be no normal force, and hence the scale would read 0. You would be weightless during the fall, but when you land again, expect to see your normal weight displayed.